Hello and welcome to this talk, and thank you for your time and interest to join here. My name is Arne Grauer, and I will present joint work with Peter Gratzer and Peter Mertes. I will talk about the chemical distance in geometric random graphs, which have long edges and scale-free degree distribution, and as a framework we will use the weight-dependent random connection models. So just as a reminder, what is a chemical distance? Well, given a graph G with vertex set V and edge set E, the chemical distance of two vertices x and y in G is then given by the length of the shortest path which connects x to y in G. For geometric random graphs, we are now interested in the behavior of this chemical distance when the Euclidean distance is large. In particular, we are interested in the occurrence of ultra-smallness, which means that the chemical distance is of doubly logarithmic order of the Euclidean distance. So when the Euclidean distance is very large, the chemical distance is still relatively small, which leads to the name ultra-smallness. Before we focus on geometric random graphs, I will give a brief review of what is known about the occurrence of ultra-smallness in non-spatial scale-free networks. So we consider a sequence Gn of random graphs, which is defined in the following way. The graph Gn has n vertices, which carry independent uniform marks. Given the marks, vertices are connected by an edge independently with probability 1 over n times some function g, which we will call the kernel function. This kernel function depends on the marks s and t of the end vertices of the potential edge. To look at two examples for the choices of the kernel function, the first one is a product kernel, which leads to random graphs as a Chung-Lu random graph, and the second one is a preferential attachment kernel, which leads to non-spatial preferential attachment networks. In both cases, the networks are scale-free, which means that they have scale-free degree distribution with power law exponent tau equals 1 plus 1 over gamma. The occurrence of ultra-smallness is here well understood. If gamma is smaller than a half, then there is no ultra-smallness, and if gamma is larger than a half, the network is ultra-small, and by Derech, Mertes in 2012, a limit theorem is established for this case. So the chemical distance is of doubly logarithmic order of the amount of vertices in the graph. So the amount of vertices in the graph here replaces the role of the Euclidean distance in the definition of ultra-smallness I mentioned before. And here also these two kernels do differ, and this happens in this constant C in the limit theorem, which is 2 for the product kernel, but 4 for the preferential attachment kernel. Why is this the case? Well, to give a short answer, to connect two vertices in a graph, the best strategy is to connect each of them to the most powerful vertex in this graph, which is the one which has the smallest mark. But whereas in the product kernel, we can connect two powerful vertices, so vertices with small mark, directly by an edge with sufficiently high probability. This is not the case for the preferential attachment kernel. In the preferential attachment kernel, we need an additional vertex with large mark, the so-called connector, which connects the two powerful vertices via 2 steps. And this doubles the chemical distance for the preferential attachment kernel. Well, now we can focus on geometric random graphs and will introduce the weight-dependent random connection model. We start with a vertex set, which is a Poisson process of unit intensity on Rd times the interval 0, 1. And we say a vertex has location x in Rd and mark t in the interval 0, 1. Given these vertices, we draw an edge between two vertices independently of any other edge with the stated probability. We already do know one term in this stated probability. This is a kernel function g, which appears here. And here it is multiplied by the Euclidean distance of the two vertices to the power d and some temperature term 1 over beta, which controls the edge density in the model. So we already know that the kernel function describes the influence of the marks on the connection probability, but what is the role of the function rho we introduced here? The function rho is called profile function, and we assume that it's non-increasing and additionally assume that it decays polynomially at rate minus delta for some chosen delta larger than 1. With this profile function rho, we are able to control the influence of the locations of x and y to the connection probability. As t and s are drawn uniformly on the interval 0, 1, the typical connection probability scales as the Euclidean distance to the power minus d delta. So with this delta term, we are able to control the appearance of long edges in our model. Now, looking at the kernel functions we already seen, first we look at the product kernel. Well, in the weight-dependent kernel connection model, this leads to scale-free percolation, or if we choose the profile function rho a little bit more general, it leads to hyperbolic random graphs and its generalizations. The preferential attachment kernel leads to the age-dependent random connection model, which is a weak local limit of a spatial preferential attachment type network, the age-based preferential attachment network. And I would like to introduce two other kernels, the sum and the min kernel, which both belong to the same model, the soft Boolean model, which is a soft version of the Boolean model, where we assign to each vertex a random radii and draw an edge between two vertices if their balls with the according radii intersect. And in the soft version, we now draw for each possible edge a heavy-tailed random variable, which decays again polynomially at rate minus delta, and multiply this random variable to the radii of the two end vertices of the potential edge. So we get new balls which might be larger, and if these balls now intersect, we draw an edge between the two vertices. So for all these four kernels, we again have scale-free degree distribution with power law exponent tau equals 1 plus 1 over gamma. But what about the chemical distance? Well, for the product kernel, analogous behavior to the non-spatial case is identified. So if gamma is smaller than a half, we have no ultra-smallness. If gamma is larger than a half, we have ultra-smallness and the same limit theorem as stated before in the non-spatial case. See Dyfan, van der Hofstad, Horimstad, Deprez, Wüthrich for scale-free percolation, and Brinkmann, Kreuch-Lengler for geometric variants of the Chung-Lu random graph, which include generalizations of the hyperbolic random graphs. Well, but what does happen for the other three kernels? Do we see an influence of the spatial embedding in terms of delta for these three kernels? And the answer is yes. This is the case. And Peter Grotzer, Peter Mertes, and me have shown that for this choice of kernel, either the preferential attachment, the sum, or the min kernel, we have non-ultra smallness if gamma is smaller than delta over delta plus 1, and the graph is ultra small if gamma is larger than delta over delta plus 1. And in this case, we are able to establish a limit theorem, which also depends on the parameter delta, which is here highlighted blue. So we have a large class of different models which now share a new behavior because they all depend on the spatial embedding, and they all depend on the choice of delta in terms of the occurrence of ultra-smallness in these networks. But why is this the case? Well, we have already seen in the non-spatial case that for the preferential attachment kernel, we do need a connector to connect two powerful vertices. But now, two powerful vertices are typically very far away from each other, and so the connector has to span very long edges to the two powerful vertices. And the existence of such edges is controlled by delta, and this strategy only works if gamma is larger than delta over delta plus 1. This weakens our strategy and actually weakens the upper bound for the chemical distance. So the main challenge has been here to find a suitable lower bound for the chemical distance, which not only incorporates the influence of the marks to all possible strategies to connect two vertices, but also influence the spatial embedding to all possible strategies. Well, thank you for your attention, and I'm looking forward to see you in the discussion session of this conference. Bye.